Welcome to the Probability and Statistics course. Today we are going to speak about the cumulative distribution function, a function that can help us calculate probabilities easily. So we are going to see the cumulative distribution function for discrete variables, for continuous variables, and we are going to see several examples. Now, the cumulative distribution function of a random variable is given by f of x equals the probability that x is less or equal to x for every x in R. This formula here, it's true for both discrete and continuous variables. It can be used in both cases. In the discrete case, we have to be careful about the equal sign. It will make a difference if we put it or not. But in the continuous case, as we have seen with the probability density function, the equal sign won't make a difference. The properties of the cumulative distribution function are that it is a non-decreasing function. The value of the cumulative distribution function at the infinity will be 0, at the minus infinity will be 0, and the cumulative distribution function at the infinity will be 1. It is right continuous, and it can be calculated using these formulas here. In the discrete case, we have to sum the values of the probability function for values xi less or equal to x. For the continuous case, we have to take the integral of the probability density function from minus infinity up to x. We use here a dummy variable, as we say, t, so that we are not confused with the x up here when we evaluate the integral. Now, from the cumulative distribution function, we can go back and calculate the probability function, then the probability density function for the discrete and continuous case. For the discrete case, it will be equal to the cumulative distribution function at x minus the value of the cumulative distribution function just before x. In the continuous case, it can be calculated by taking the derivative of the cumulative distribution function. We are going to work through an example. In the discrete case, we have two dice. Here, we throw the two dice. We have the sample space here. There are 36 outcomes. We have colored the dice red and green, as we have said before, and this is our sample space. Our random variable is that x is the sum of the two dice. We're interested in the sum of the two dice. Now, in this table, we have the probability function. X is 2, 3, 4, up to 12. We have seen this in the previous lesson, and we want to calculate the cumulative distribution function of x for these values. We know that before 2, the cumulative distribution function will be 0. It will be 0 as there are the f of x will be 0 up to 2. So no matter how many zeros we add up, the cumulative distribution function will be 0. At exactly point 2, we have 1 over 36, the probability that x takes the value 2. So the cumulative distribution function becomes 1 over 36. In the same way, the cumulative distribution function is 1 over 36 for every value between 2 up to 3, not including 3. At exactly point 3, the cumulative distribution function becomes 3 over 36. We are going up to point 12, where we can see by adding up all these probabilities, we have that the cumulative distribution function will become 1. For all values greater than 12, the cumulative distribution function will remain 1 as f of x is 0 after that. So we don't add up any other probabilities here. How we have calculated the cumulative distribution function, we see here, for example, the cumulative distribution function at point 3 will be the probability that x is less or equal to 3. We see here that the equal sign makes a difference. We have to be careful if we need to include the equal sign or not. In this case, we need to include it as we want the cumulative distribution function at 3. So this is equal to the probability of x equals 2 plus the probability of x equals 3. From our table we have seen before, this will be 1 over 36 plus 2 over 36 will be 3 over 36, as we have seen in our table. Here, our table again, we see that we have calculated the cumulative distribution function and it's 3 over 36. So now we see that what actually this means is that the cumulative distribution function, in other words, is the sum of xi for xi less or equal to 3, f of xi. Because for all other values f of x will be 0 and only for x equals 2 and 3 is not 0, this means that this is equal to f of 2 plus f of 3. And we find again that this is 3 over 36. Now, we can derive the cumulative from the cumulative distribution function f of x. We go back to our table. We see here that the cumulative distribution function, as we found before, has these values. So we can calculate, for example, that f of 3, in this case, as we said before, it will be the cumulative distribution function at point 3 minus the cumulative distribution function just before 3. And just before 3 it was 1 over 36. We said that the cumulative distribution function remains 1 over 36 from point 2 up to, but not including, point 3. So we calculate f of 3 is 2 over 36. And in this way, we can fill in our table. A graph for the cumulative distribution function is here. For this example, and that's the picture we're usually going to get, a picture with some steps as we see, is the case, the picture we get for the cumulative distribution function when we talk about discrete random variables. So here we see that the cumulative distribution function gets a value at exactly point 2 before it's 0. It remains this value up to point 3, but not including point 3. At exactly point 3, it makes a step. That's why it's called a step function, and it goes up to this value. It remains this value up to point 4, but not including point 4, and makes a step and goes up. And so we go up to 1. So here we have the value of the cumulative distribution function becomes 1 and remains 1 for the rest values. Now, we see some of the properties of the cumulative distribution function. As we said before, the cumulative distribution function is right continuous. So we see that as we go down, we have always values for the cumulative distribution function that do not change. It is a function that is non-decreasing. That means it's always increasing the values or remains the same. And also, as we said before, the value of the cumulative distribution function at minus infinity is 0, and at infinity becomes 1 and remains 1. Now we are going to see an example for the continuous case. We measure the length of the next phone call in minutes. We assume the length of phone call has probability density function given by this formula. This formula tells us that for x greater than 0, it can be calculated from here, and is 0 for values of x less or equal to 0. So we want to calculate the cumulative distribution function, and we have that. We need to take the integral of f of t dt, as we have said before, for minus infinity to x. Now in this case, in the continuous case, we do not need to take each x and calculate the cumulative distribution function. We can actually find a general formula for any x. So for here, as f of t is 0 for values between minus infinity and 0, we are left with this integral here, which is from 0 to x of f of t. And if we calculate this, we find that the cumulative distribution function will be 1 minus this quantity here. Now the cumulative distribution function is 0 for x less or equal to 0. We can see that from our integral as well, because we'll go for minus infinity to some x less than 0. This is always going to be 0, so this can be calculated to be 0. The cumulative distribution function can be used now to compute the probability that a phone call will last less than 7 minutes. So we don't need to do any calculations to find this probability. We can use the cumulative distribution function and find that f of 7, if we replace in the formula where x the 7, we find that this probability is 0.5034. Now to find the probability that a phone call will last longer than 2 minutes, we calculate the probability of x greater than 2, which is equal to 1 minus the probability of x less or equal to 2. We remind here that the equal sign does not make a difference. We have continuous random variables, and this will be equal to 1 minus f of 2, which can be calculated and is found to be e to the minus 2 over 10. So we see how the cumulative distribution function can be used to calculate probabilities for the discrete and continuous random variables when we want to find the probability that x less or equal to some number, or the probability of x greater or equal to a number. Now we are going to see how in the continuous case we can derive the probability density function from the cumulative distribution function, and we're going to see for this example we have worked how we can do that. So we can calculate, given the cumulative distribution function, the probability density function for the example we have seen, and that is given by we take the derivative of the cumulative distribution function, the derivative of 1 minus e to the minus x over 10, and we have that this is equal to 1/10 e to the minus x over 10 for x greater than 0 and for x less or equal to 0. We have seen in the discrete case that the cumulative distribution function is a step function. Now we are going to see a picture of the cumulative distribution function for the continuous case. So we have here, for the example we have seen, that the cumulative distribution function is not a step function in this case. It is a continuous line, and it reaches 0 at 0, as we have seen, and goes to 0 in the minus infinity. Also, it is a non-distributive decreasing function, and it is going to go to 1 asymptotically at infinity. We also see that it is right continuous. In this case, for the continuous random variable, it is left continuous as well. So we have seen how we can use the cumulative distribution function to calculate probabilities, to calculate the probability that x is less or equal to a value, or greater or equal to some value, and in the discrete and the continuous case. Now we are going to work through an example, and we have that we consider the example we saw in the last lesson. We have the probability density function given by f of x equals b over 2 e to the minus b absolute value of x. X will belong in the interval minus infinity to infinity, and we know that, we have said that we have b greater than 0. Now for this example, we are going to calculate the cumulative distribution function and then use this to find probabilities when we want to find, for example, the probability of x less or equal than 2, instead of using the probability density function to find these probabilities, as it is more difficult to do this. It would be much easier to use the cumulative distribution function. So we have that we have to take two cases in this example, as the formula here will change depending if x is positive or negative, and we have that f of x from the definition is the integral which has to be evaluated for minus infinity to x. In here, f of t will change depending if we are at values at positive values or at negative values of x. So if x is less than 0, the cumulative distribution function, this will go from minus infinity up to a negative value, will be f of t can be replaced by beta b over 2 e to the minus b times minus b times minus x, which is b times, we change x to t as we are talking about f of t here, so that we are not confused with the x in the integral, and we have to evaluate this integral. So this will be equal to b over 2, this, the integral of this will be e to the b t divided by p from minus infinity to x, which is equal 2b over 2 e to the minus e to the b x. X takes the value of t there. B minus, if we put minus infinity in t, we have 0, and that will be equal to half e to the b x for x less or equal to 0. As seen in this example, we have to be careful for what x do we talk. So if our probability density function changes at some point, we have to split calculating the cumulative distribution function depending on how the probability density function changes according to values, different values of x. So we now are going to calculate the cumulative distribution function for x greater than 0. So we have that if x greater or equal to 0, f of x in this case equals minus infinity to x f of t dt. Here f of t, as x is greater or equal to 0, will change, will be different depending if we are at negative numbers or we are at positive numbers. So we are going to split this integral to values of x up to 0 and to values of x greater than 0. So this will go from minus infinity to 0, f of t dt, plus we have the rest from 0 to x, x is positive, and we need to calculate separately these two integrals. So this we can calculate is, we have minus infinity to 0 b over 2 e to the minus b times minus x. It is a negative number, so we also calculate from 0 to x b over 2 e to the minus b x dx. And we do the calculations. Here we can find that this is half plus this integral here. Now this half could be calculated in an easier way. Instead of evaluating this integral, we can actually use the cumulative distribution function we have found for x less or equal to 0. We see here that if we put x equals 0, this will give us that f of 0 is half. the value that we are looking for. So we can see in examples like that, we can use the cumulative distribution function when calculating cumulative distribution function for following steps. And here we have half plus, we calculate now this part, which is equal to, we do the calculations for the integral from 0 to x, and this will be equal to half plus b over 2. We have from x to minus divided by minus b, and this, if we do the calculations, we can find that it is half plus half 1 minus e minus b x for x greater or equal to 0. When we have finished working with an example, I have calculated the cumulative distribution function. It is nice to write down everything together. So if we want to use the cumulative distribution function, we can easily find at which point of the which formula of the cumulative distribution function we should use depending on the x we want to calculate the probability. So for this example, we write that the cumulative distribution function, everything we calculated, we have two cases. We have x greater or equal to 0, and we have x less to 0. Now it doesn't matter if where we put the 0, if we put it here, if we include it in both cases, the formula should agree. The two formulas should give us the same number. So for x greater or equal to 0, we have the cumulative distribution function equals to half. We rewrite what we have calculated, and remembering what we have calculated before for x less than 0, we have from here that it was half e to the bx. We transfer it at our formula, and we have all information here in our table. So now it is easy, if we want to calculate a probability, to consult our table we have written down and calculate from the cumulative distribution function the probability. For example, if we want in this to find the probability that x is 3, let's see, that x is less or equal to 3. So this is actually the probability of x less or equal than 3. Now, we consult the table. We see that 3 is greater than 0, so we should use this part of the cumulative distribution function, and this will be equal to half plus half 1 minus a to the e to the 3 times b. Given a value of b, we can calculate this number. So we can see here that the cumulative distribution function is a very useful function when working with probabilities. In most cases, actually, it is much easier to calculate from the probability density function of or the probability function in the discrete case, the cumulative distribution function, and then calculate probabilities rather than using the other functions without calculating the cumulative distribution function. So here in this lesson, we have seen the cumulative distribution function for discrete variables and for continuous variables. Actually, the formula it's the same, although we have seen that they look very different. One is a step function and one is not. It is a continuous line. We have seen examples and we have seen why the cumulative distribution function is so important, is so useful in order to calculate probabilities. If for more information about this lesson, you can visit the web page of UNINETTUNO MedNet Youth project.